Hello guys. Now we are going to discuss on how to classify data sets that have more than a single class. I will open another terminal here, and this video is a short video just to make sure you guys try to use my code or this code we developed together properly. If I consider the iris dataset, which is a very basic dataset, I already have three classes: Virginica, Versicolor, and Setosa. What I suggest you guys is this. You guys know which are the elements in this fifth column, equals to Setosa. You know which are the elements equal to Virginica, and you know which are the elements Versicolor. First of all, you are going to create a sample based on the class. You are going to build up a classifier for it. For instance, I will build a classifier to separate Setosa from the others, another to separate Virginica from the others, and a third to separate Versicolor from the others. So my role here is to tell you, to teach you how to classify a multi-label or a non-binary, let's call it this, a non-binary data set. Okay? In that scenario, I will consider iris because it's easy and quite simple to understand. We know this data set has three possibilities. But consider I just don't know. What I should do is something like this. First of all, I need to take the number of columns of this data set, and I will consider the last column to represent my class index, okay? Based on that, I will, of course, ask for the unique elements related to classes. So here I will have the unique elements, or if you prefer, the classes we have. Okay? After having the classes, I will have a loop per class. We're going to build up a first classifier for the first class, a second classifier for the second class, and so on. So building up a classifier for class equals to classes I. Okay? That's our task. Of course, here I could call that function tune dot, it's just tune. This function tune is actually our function inside this file, tune SVM, this function here. If you guys remember, we discussed the function in the previous video. So I'm gonna copy the header, of course, just to bring here and think about the parameters. I will need to define some holdout, okay? I will come up, I will try, maybe I should, yeah, it could be like 70%. Which are the kernels I will be considering? You know, I will just consider the polynomial. Let me think. I will not consider the sigmoid kernel. I will consider linear, polynomial, and radial. Cost could be 100. Gamma, yeah, could be two values for gamma, two values for degree. You know what? For degree, I will just set 2. And for coefficients, yeah, two values are good just to have the opportunity to try a homogeneous kernel and a non-homogeneous kernel. And here we are going to have the tuning results. Tuning results. What I'm going to do with those tuning results, I just get this guy and look for a particular column which is accuracy. And I want which is the maximal accuracy and bring the ID of that particular table. From that, we will have something like this. In that particular row, we are going to have the configuration or the setting. The setting will bring something for us. Let's see at the end of this file. It's going to provide the kernel. So of course, setting $kernel will bring the best kernel for us. That's a best kernel. If it's linear, if it's doesn't matter. If it's polynomial, radial, okay. It's going to provide the cost for us. It's going to provide also the values for gamma, for degree, if it's polynomial, of course, sorry, and also for coefficient 0. Okay? What is interesting is this: if the kernel is indeed linear, I will model according to the linear kernel. If it is a polynomial kernel, I will model as a polynomial kernel in my final version. If it is a radial, I will model properly as a radial. Okay? That's what I need to do. And of course, if it's a linear, I go back to this file up here. If it's linear, let's see. Yeah, that's what I need to provide. I will bring this. Oh, sorry. This. Copy and bring here. Okay. That's how my model is going to be obtained if it is linear. Okay? Let's suppose it's not linear. It is polynomial. That's how we are going to build it. Copy and bring it here. I'm just copying to remember the parameters, guys. Okay? If it's radial, of course, this is the way to go. That's the way to go. Okay. Great. I'm going to close this file up here and just stick with my optimization. So for each class, just let us know what is the class. Over here, I need to build up the training and the test sets. We're gonna build like in few instances. And of course, my X here will be X train, my Y will be Y train, because that's the name I will give for those two sets. Then I run my tuning. And of course, after tuning, we will have the greatest accuracy and of course, the proper setting for our model. Here, no, not here, could be later. Okay, now what I'm going to do is this, run my SVM, setting my cost. If it's linear, my cost will be setting cost. Take a look here, just to remember. If it is a polynomial, it will be setting dollar gamma here, and here dollar degree, okay, and here dollar coefficient 0. Oh, I'm just forgetting about cost. Sorry, over here. And setting dollar cost. Yeah, that's all. Maybe we could bring this to here and maybe perform just trying to use less rows. Okay. And here it will be setting gamma, and here setting cost. So what is interesting now is this. We have a data set with 3 classes. We're going to get the first class, build up a training and a test set, optimize to find the best kernel for that particular class, to separate that particular class from the others. Then we're going to build up the model. This model will be a list. And you know what? I'm going to do like this. Model indexed in terms of I. Model indexed in terms of I. So that will be our model. I. Wow, that's so good, because now we've got all our models. So we're going to have 3 models for a 3-class dataset. Just drinking some water, it's so hot. Wow, terrible. Okay. Of course, I need to build up my training, my test sets. What can I do? I should take my data set in that particular column, which is related to my class, and check out how many elements I have for that particular class, and how many elements do not belong to that class. Then I will take the minimal for that. Why the minimal? Because I will consider the class having less elements. So in this scenario, my class, for example, equals Setosa will be my positive label. And all the remaining classes will be considered as my negative label. When I run for Virginica, Virginica will become my positive label, and all the remaining classes the negative label. If you guys remember, Iris has 150 examples. Okay? So, of course, I will have 50 belonging to this class and 100 to the others. So the minimal will be 50. So, of course, here I'll have the minimal value. Okay, that's good. What I'm going to do with that? I'm going to take that and multiply that particular value for my training sample size. So over here, I will decide what is the size of my holdout. Suppose my holdout will be equals to 70%. So here I will multiply this by holdout, and I will round up to get that as my number of examples to build up my training set. So build up my training set from 1, sorry, not from 1, even easier. Consider all elements belonging to this class and select all elements belonging to this class. So which are the elements belonging to this class, and select 70%. That's going to be the size of my selection. So those are the IDs of my training set, or maybe train or training. It could be train IDs, just train. Okay. What I'm going to do with my test, I'm going to copy this basically, and here I will have test IDs. Test will be select also, from the elements that do not belong to this class. You are also going to select this number of elements. So I will have the same amount of elements belonging to the class itself and to the other classes. Okay. What I'm going to do now is this. My training set xtrain will be iris from the first to the fourth row, identified by train IDs. My ytrain will be iris at the fifth column, exactly like that. But there is an issue over here. Oh, sorry guys. This is not test IDs. This is also train IDs, but actually I will compose with the train IDs that were selected here. Because in this way, I will have the same number of elements belonging to the class, the positive class, and the same number belonging to the negative class. Sorry, that was my bad. Okay? And of course, I will have y here. What is interesting about y is something else. Whenever the element belongs to the class itself, my label will be +1. And when it belongs to a different class, my label will be -1. So what I'm going to do here is not just like this. It's not this. I could do something different. We could do this. Select the positive and select the negative. I think that's even better, because now I don't need to compose and concatenate those elements. I can do like this. Here, you're going to select the positive followed by the negatives, like that. And here, you are going to create a vector with positives for, let me think. Yeah, I think this is right. For the number of elements I have in the positive set, and a repetition of -1s for the number of elements belonging to the negative set. So we have positive, the training sets. Oh, you know what? It's not even necessary, guys. Sorry, that's my bad. Because here we are already building up the training and test sets, right? Inside this tune. But there is a problem. Inside this tune, we are just holding out 70%. You know what? I think I will just set hold out here as 70% as it is in here, okay? And I will not create this. I will do something different. I think it's going to be just easier for us if I do something like this. Just consider which are the elements from the iris data set belonging to this last column, which are equal to classes I. And you know what? Those are the elements that should be positive. All the others should be considered as negative. You know what I'm going to do? I'm going to create y here. It's going to be a repetition of minus ones by the number of rows we have in iris, which is 150. And you know what? I'm going to take at those particular IDs and change to positive one. I think that's even easier. Why that's easier? Because now I can just run, you know how? X is going to be iris from 1 to the 4th column, and this will be considered as a matrix. And now X will be X fully as an argument and not X train. So here inside 2, we are going to perform the holdout. Of course, this holdout will select 70%, and 70% sometimes will have for sure, will have some sort of imbalance. What happens when in imbalanced situations? As we have 1/3 of the examples belonging to the class Setosa, 1/3 Virginica, 1/3 Versicolor, when we select 70% for training, that training will have around 2/3 of negative classes and 1/3 of positive classes. The most perfect way of performing that is balancing the scenario, is by considering less than 2/3 here. It's considered 1/3, 1/3. But I'm not going to do that at this stage, okay? The remaining 30% is going to be used for testing, like that. That's our scenario for now. Okay, so we are going to perform this assessment, select the best model, and at the end we're going to have the models. The models. That's what we're going to have here. One per class. Okay, let's load my code. What's the name of my code? I have no idea. Non-binary. Oh yeah, there's a problem here. It didn't find tune, this function tune. This function tune belongs to a code we wrote together, which is tune_svm.r. So I need to load it like this, okay? So now let's try it. Wow. Yeah, there's a mistake here. It's not X train, it's just X. Sorry guys, here. Just X and Y. X and Y. And X and Y. Sorry, my bad. Okay. So, yeah, it's running, but there is a mistake over here. What is the mistake? Error in gamma X transpose X dot product transpose X. What is the problem with that? You know what? I think I'll just print turning here. Not print, return it. I think it's even better, because you can see what's being returned. Oh, there's no return here because this is not a function, sorry. So I'm going to print out and just stop the execution with a small mistake over here. And running, yep, that's good. Yep, we've got, oh, accuracies are amazing actually. Oh, okay, yeah, accuracies are impressive for this, yep. Okay, 100%. So for this is for the first model, okay guys? For the first model, we've got 100% of accuracy in all those elements. You know what? If I've got something like this, what happens when I apply this maximum? Let's see. Let's print my ID and let's stop the execution here. I think it's going to select the first kernel, which is the linear kernel. Yeah, it selected the first. which is the linear kernel. That's a good selection because it's just an easier kernel. Of course, you guys could also consider the sum of x's and the number of support vectors. I'm not considering, I'm just considering accuracy at this point, but you guys could consider that. So what's going to happen with setting? Let's print setting out. I think there is a mistake here, probably. Let's see. Running. Yeah, it's here. Yeah, it looks good. Kernel, linear, cost 100. Let's print. Maybe instead of printing like this, I'll print like this. Dollar linear, dollar kernel, dollar cost. Yeah, that's all. And just stop here. Let's try loading my code once more. Yeah, linear 100. I know, guys, what is happening. You know what? When I take this cost here, it is, as you can see here, it is as a string, as a character, a vector of characters. So here I should have translated to a numerical vector. The same happens here. I should have translated this into a numerical value, gamma. Here also, as a numerical value for degree. And of course, here it happens in the same way as a numerical value. I think that's all. We're gonna see. Here also as a numerical value. Okay, that's pretty much good. Oh, sorry. And here also as numeric gamma, and here as numeric C, as numeric cost. Let's see what happens. Reloading my code. Wow, it's running. That's perfect. Yeah, it converged perfectly. If I go back here, first model, 100% of accuracy. Wow, that's amazing. 100% of accuracy. Best model. All those were good enough, but we selected the first. It's always better to select a linear kernel, of course, because it's simpler in terms of comparison of spaces. Second, wow, it wasn't the kernel, the linear kernel. Actually, it's going to get the first accuracy equals to 1. So it's going to get this guy over here. The greatest value happens here. But you can see the number of support vectors happens to be better here, because you have less vectors and a smaller value for the sum of C's. There is a kind of conflict over here, because if you decide in terms of the number of support vectors, you're going to get this solution. If you decide in terms of C's, you're going to get this solution. But you can compose, you can give like different weights for the accuracy, the support vectors and the sum of C's. So of course, in this scenario, it's going to get this second order polynomial kernel. And finally, the last class will consider the linear kernel as well, this linear kernel as well. You know what? Now, you guys will have 3 modules. A module for the first class. This is the model for the first class. I know you can see like some values for alpha, some values for, take a look, values for alpha, values for zeta, values for C. But at the end, you must remember, okay, this is a linear kernel. So if I try to perform a classification, I must call classify linear. And here, provide x, provide y, and provide my x mu. The second is a polynomial, so I should use classify polynomial instead. And the third is linear, I think. Yeah, so it's classify linear. What are the classes? If you go back here and consider these variable classes, you're gonna see the first model is related to setosa, the second to virginica, and the third to second to versicolor, and the third to virginica. So the first is going to classify setosa, the second versicolor, and the third virginica. So what I suggest you guys, now as homework, you're gonna carry on this code to perform a classification on part of your data set. So instead of considering the whole data set to perform this tuning stage, you're gonna get an extract of your data set to perform the tuning stage, and then you're gonna assess your classification in a different subset of iris. You're gonna apply for every X new you have, you're gonna apply the first model, the second model, and the third model. What you are going to have? You are going to have a particular result for the first model, a result for the second model, and a result for the third model. How are going to be those results? For instance, if this guy is like positive 10, it means the first module placed this guy on the positive side, and of course very, very far from the hyperplane. Let's suppose this guy is going to place in the negative side, but very close to the hyperplane. And this guy is going to place you very positive, but very close to the hyperplane. What is the best solution to go? Of course, it is this one, because it is by far the most distant solution from the hyperplane. You probably remember this from the previous classes. Please, guys, do that as homework. See you in the next video.